to page 273, we can highlight a little bit about what we saw already. So first of all, adding functions, some of the key things that I want you to see here is notation. This notation right here, f of x plus g of x, is the easy notation. It's really intuitive. It really looks like I'm adding the graph of f plus the graph of g. Sometimes, though, it's also written in this notation, where the f plus g is written in brackets with the x afterwards. So in that second set of notation, where it comes up and that sometimes students find it confusing, is if you see something like this. What does that equal? According to these graphs here, we've got our g of x graph, that's the blue one, and our f of x graph, which is the red one. I want a number for this answer. One. So what I would suggest is if you have this other notation, I would take a first step and change it to the notation that you are more familiar with. This notation is exactly the same as that notation. And then when figuring that out, well, f of 2, if I look at the red graph, f of 2 is equal to 2. G of 2, that's equal to negative 1. So then you could figure out that adding them together would be 1. And that was one of the main strategies we found out before in the math lab of how do I add up two graphs? Well, I'm going to add the y values, and I can add the y values by finding nice points. Those, when x is 2, would be example that there's two nice points it's easy to add together. And when you do, you would get this green point right there. Your x value stayed the same, and you just added up your y values. And so if you do that with all your points along the way, this is the graph that you would get. So for example, another nice point would be this one, where y is 0, and this one, where y is 3. 0 plus 3 would be 3, so we get that point for our green graph. Do that all the way along, and you get an idea of what that graph looks like. Now, another thing that we noticed with our graphs yesterday is if we're talking about our domain, in this case, the blue graph has a domain of everything, and the red graph only has a domain when x is bigger than or equal to negative 2. Then our green graph, which is adding them, has to have that same overlap of those domains. And that's something that's true for adding, subtracting, and multiplying, that the domains had to overlap. But where it was different was with the dividing, right? Because you might also have non-permissible values. So we'll look at that after. But first we'll look at the adding, subtracting, and dividing. Nice. So again, we can take out our highlighter here. Subtracting functions, here's the notation that you're used to. Here's a notation that means the same thing. So now if we look at that same x value when x is 2, what would f minus g be? Well, you could write it in the other notation. F of 2 is 2, g of 2 is negative 1, and so we will get 3. And that matches up with that point right there. So again, we're subtracting our y values. We're finding nice points to do that. And also, once again, the domain overlaps. So the domain of one was everything. The domain of the other one was x bigger than or equal to 2. So the domain of our green graph is where they overlap. And finally, for multiplying, same thing. Different notations. And with the multiplying, you might even see it on an exam like that. Any kind of multiplication symbol in between. So again, find nice values, multiply them together, do a bunch of points. Now with multiplying, we also talked about, besides the nice point strategy, right? There was the nice point strategy where you tried to find two nice points, like that blue and red one that gets us this green one. But there are also some points that you can find where it only has to be nice for one of the functions. For example, this point right here. That'll be a point you'll always want to check. You'll want to check, where are my red graph or my blue graph, my original graphs, equal to 0? Because 0 times anything is 0. So even though at this blue point right here, I would say that our red point isn't a nice point. It's not something that you can easily, you'd have to estimate to figure out what that is. We still know that 0 times anything is 0. Yeah. The amount of points you have to have is really dependent on what graphs you start with. Sometimes you might be able to tell right away that I'm multiplying two functions, it's going to make a parabola. And then you're going to need less points because you know certain properties of that graph. Here, we're multiplying a line by a square root. That doesn't end up with a graph that we've graphed a lot of. And even if we look at that final green shape, it doesn't look like something that we're used to. So in situations like this, you're going to need some more points. So in this case, if I label things, this is a nice point, this one had nice points. After that, I would say this is where it's 0, but I wouldn't feel that that would be enough points to be comfortable with. So how do we find some other points and some other properties of multiplying to help us with this? Another point that I would do on this one, or another 2 points I would do on this one, is this green one and this green one. Now I want you to look at those 2 points and tell me, what do they have in common? This is telling us P is the green graph, because they have defined it right here. P of x is equal to f of x times g of x. So P of 2 is equal to f of 2 times g of 2. Well, P of 2 is function notation. That's saying when x is 2, what's y? And P of 2, in this case, if we look on our green graph right here, P of 2 is equal to negative 2. So this is just there. Here's the y value, and here's the function way of saying the y value. Normally what we would probably do if you were showing your work, and I think what you're confused about how it's shown here, is normally you would probably start like this. P of 2 is equal to f of 2 times g of 2. And I know that f of 2 is 2, and I know that g of 2 is negative 1. And this multiplied together is negative 2. So I know that P of 2 is equal to negative 2. And that's normally how you would probably write it. They've done something similar, but they started with this, said it's equal to this, it's equal to this, and since this is equal to P of 2, this is equal to that. And that's the notation that they've used. So those 2 green points that I just drew, this one here and this one here, would be the next 2 points that I would graph if I was multiplying those 2 functions together. What do those 2 points have in common? One of the graphs has a value of 1. Can you see on the first one right here that the red graph has a value of 1? 1 times anything stays the same. So that's why I drew it exactly where the blue graph was. And then here, now the blue graph is equal to 1. So 1 times anything would stay the same. So I can say that's where my green graph would intersect my red graph. And so those are some other values that you could do to give you a sense. Now once we had these points, then it would be pretty accurate to draw your graph. So there isn't a set, oh, I need 2 points, like in transformations or some of the main graphs that you got to know the shape of them, you only needed 2 points. Sometimes in these ones you're going to need some more points just to get a sense of what the shape is. And you're always going to use any nice points you have, so use them all up. If you have 5 nice points, do them all. It's not that hard to do. You're going to do any points where it's equal to 0, because 0 times anything is easy. And then if you're feeling like that wasn't enough, then this idea of looking for where one of the values is equal to 1 can give you another couple of points. If that's still not enough, then you can estimate using not nice points. So what does estimating using not nice points look like? Well, it looks like no matter which point I choose on this graph, the blue points are nice, right? So if I went when x is equal to 3, there's my blue point, there's my red point. My blue point is at -2, my red point is at 2.2. So if I did 2 times 2.2, I'd get -4.4, and so I could draw that on there as well. It's not nice points, but I'm using an estimate, and it's still going to be fairly accurate. Again, the domain overlaps. So let's look at example 1. We've got f of x equals x plus 2. I will make that my blue graph. And g of x equals the absolute value of x. I'll make that my red graph. In part A, we want to find the domain and range of each of those. So for f of x, the domain is everything because it's a line, and the range is everything. So both the red graph and the blue graph are graphs that we know. So when we think about g of x, that's an absolute value graph. That looks like this. Again, the domain is everything. And the range is bigger than or equal to 0. Now in part B, we're going to add those functions together. We want to find an explicit equation for h of x. So here is some words that we have to make sure that we know what they mean. And an explicit equation, what that means is we want to write an equation with only x's. Right now, h of x is in an equation. This is not an explicit equation because it's written in terms of the functions. So an explicit equation is written in terms of x only. So we can do that simply by saying, well, I know that f of x was x plus 2, and I know that g of x was the absolute value of x. This would be an explicit equation. And you might look and say, can I simplify this anymore? Can I put any like terms together? And in this case, absolute value of x and x, they're not like terms. So we can't put them together the way that it's written right now. Now, the domain part of h of x here, well, that's just going to be an overlap of the two domains that you had from before. So when I look at my domains of my red and my blue graph, My domains were everything. So my domain of this graph is going to be everything. The range, however, is not as easy to just say, oh, is the range going to be an overlap? No. For the range, you're going to actually have to try and add these graphs together and see what happens. So let's draw a quick graph of what h of x looks like. And you have an explicit equation of that. Sometimes the explicit equation that you get is going to be a graph that you already know how to graph. Maybe it's just a simple line. Have you ever graphed anything like this before? X plus 2 plus the absolute value of x? No. So what do we go to when we have a graph that we've never seen before? Sorry? We could go to our calculator, but if this was a non-calculator question, could you tell me one point that could be on this graph? Okay, when x is 0, what's it going to be? 2. Good. So you just plugged in a value and figured that out. That's a table of values. How many more values could you get that way? A lot. So let's get a few more and see if we see any patterns. What would another x value you'd like to plug in? 1. If you plug in 1, can you see that you're going to get 4? Plug in 2. You get 6. So far, it's a straight line. Will it be a straight line forever? Where is it going to have a problem? To the right or the left? So tell me a value to the left you'd like me to plug in. -1? If you plug in -1, can you see that this is going to be -1? This is going to be +1. They're going to cancel out. You're going to get 2 again. What would happen if you plugged in a -3? This would be -3. This would become +3. They would go away, and you would just get 2 again. Can you see that no matter what negative value you put in, it's always going to be 2? Well, we draw an asymptote when our graph gets close to a line but doesn't touch it. This one just stays at 2. So it's just going to be like a straight horizontal line. And it's going to be a straight line this way. So this graph kind of looks like two graphs stuck together. A graph of one line and a graph of another line. Would you agree that you could write the equation of this line as y equals 2? And the equation of this line, well, it looks like it has a slope of 2 and a y-intercept of 2. So I could write the equation of that line as 2x plus 2. Now, when graphs are like this, that they sort of come in 2 different pieces or 3 different pieces, they actually have a name for these kind of graphs. They're called piecewise functions because they can be written in different pieces. And so sometimes this is an explicit equation for h of x. Sometimes you could write it in those 2 different pieces. So what would that look like? This graph is equal to 2 when x is less than 0, and it's equal to 2x plus 2 when x is bigger than or equal to 0. These 2 equations mean the same thing, just written in 2 different forms. Now, we got those 2 equations by plotting all of our points and figuring out what it would look like. Another thing, let's see, it was g of x. G of x was equal to the absolute value of x. The absolute value of x is another function that could be written as a piecewise function. Because if you think about it, does it make sense that the absolute value of x looks like 2 different lines pieced together? Sometimes The absolute value of x is just x. When does that happen? You plug in a number, it stays the same. What do I have to tell about x? Like if I plug in 5, it stays 5, right? If I plug in -2, it becomes 2. So I want this part here. I'm saying if I plug in a number and it stays the same, what do you know about that number to begin with? It had to be positive, right? Bigger than or equal to 0. How would I write the equation for the negative ones? If I plug in -3, it becomes +3. I could write that by just multiplying it by a negative. Whenever x is less than 0, it's a negative x. We could have used this algebraically, this piecewise function algebraically with our original function. If we were thinking about x being less than 0, then I could have said this is going to be negative x. And x plus negative x is 0, and we just get 2. If x was bigger than 0, then this is going to be positive x, and then x plus x is 2x plus 2. So we could get our piecewise function by examining the equation more closely and thinking of the absolute value one that way. So after that, of graphing it and analyzing a little bit, the whole reason we did that was to see if we could figure out the range of h of x. Now that we look at our graph, what's our range going to be? Greater than or equal to 2. So g of x is originally our red graph. It's equal to the absolute value of x. And here is the graph of it. I should do it in red because it was our red graph. There we go. That's the graph of g of x. And just like the graph of h of x, you could imagine that being two straight lines being pieced together. So we know that the equation for g of x is the absolute value of x. And I introduced you to this new notation called piecewise functions, where when you have a graph that you can see two different equations pieced together, you can write it as the two different pieces. So how could I write the red graph as my two different pieces? Well, if I start with this line on the right, that line is just y equals x. So I write that there, but that I have y equals x only when x is bigger than or equal to 0. And I have this part on the left is y equals negative x, and I have that graph when x is less than 0. So in a piecewise function, you have the two different equations, but you have to specify what domain I draw one graph and what domain I draw the other graph. In part C, we want to multiply these two together. So P of x is equal to f of x times g of x. And again, they say, can we write an explicit equation for this? Well, f of x is x plus 2, and g of x is the absolute value of x. Whoa, I decided to use a pen that disappeared. There we go. So again, that's not a graph that we've seen in the past. And so if we wanted to graph this, we could start by plugging in some points. What would be a nice point to plug in? 0. Going to get 0, 0. What happens if you plug in 1? (1, 3). What happens if you plug in 2? 2 comma 8. What happens if you plug in negative 1? Negative 1 comma 1. What happens if you plug in negative 2? That'll be 0 again. So if I had just given you the points and you didn't see the equation, and I said, what kind of graph does this remind you of? An x cubed graph, okay? But if we look at the equation, is there any way to get an x cubed out of that? No. So I'll show you what this graph looks like. According to the dots, yes, it does look like a bunch of x cubed graphs, but in reality, this graph has a sharp point there. So this graph has a sharp point here instead of a nice rounded point like an x cubed graph. So why does that happen? Well, if we look at the piecewise function for this graph, and remembering that this absolute value graph is already a piecewise graph when x is bigger than 0 and when x is less than 0. We're going to start. When x is bigger than or equal to 0, what happens to the absolute value of x? It's just x, right? And if I had just x here, what would happen if I multiplied this out? Can you see that you would get x squared plus 2x? And when x is less than 0, what is the absolute value of x equal to? It's not still x, because if I plug in negative 3, I don't get negative 3. It's negative x. Does that make sense? And so if this is negative x and I multiply it out, can you see that you would get negative x squared minus 2x? If we think of those as separate pieces, can you see that they're two parabolas? Okay? I'm going to draw that parabola with a dotted line over top of our graph. This is what it would look like. I'm going to draw this parabola with a dotted line over our graph. So if I only took part of this parabola when x is bigger than 0, and part of this parabola when x is less than 0, that gives us our final graph and explains a little bit why it's so sharp at that point. So I got these two different parts by saying what happens, and I'm going to just move the screen up here a little bit so you can see g of x here. That's our red graph. So the absolute value of x, when written as a piecewise function, is sometimes x, sometimes negative x. When x is bigger than 0, it's x. So when x is bigger than 0 here, I just made this an x. And if you multiply x times x plus 2, you'll get x squared plus 2x. In the second one, if I said when x is less than 0, this becomes negative x. If I distribute that negative x, when x is less than 0, I'll get negative x squared minus 2x. Now that we have our graph, again, the domain part, which is usually what they'll ask on an exam, because the domain part is the easy part. It's just the overlap of the two original functions. And since the domain of both original functions was everything, the domain of our function will be everything. The range is a little bit harder to find out because you have to graph it or you have to analyze the graph and figure out what the different pieces are. In this case, the range is everything as well. Okay, questions for practice here are 3, 5, and 10.